Welcome to EDU World Space.
In this question, we have a smooth sphere of radius r. A particle with mass m is held at an angle of 30 degrees to the vertical. It is then released. The first part of this question wants us to find out the force exerted on the particle by the sphere just after it's released. So we know at this point this must be equal to the normal contact force on the sphere. As a result, we must resolve the weight of the sphere in the direction of the radius to find out the normal contact force. So what we know is that this angle in here is 30 degrees. This is the radius, and as the normal contact force acts vertically downwards, this angle in here must also equal 30 as it's parallel to the vertical. So due to alternate angles, this is equal to 30 degrees. So as a result, for the first part of this question, we can say that the force acting on the small ball due to the sphere is equal to the radial component of the weight of the small particle, so is equal to mg cosine 30, which is equal to root 3 over 2 mg. So that is our first answer. The next part wants us to find out at which angle the ball leaves contact with the large sphere. So this is the point that the ball is no longer in contact with the surface, and therefore the normal contact force must equal 0. As we know that the normal contact force is equal to 0, this means that the resultant radial component of the weight of the small particle must equal the centripetal force to keep it moving in a circle. So we can equate these two expressions and say that centripetal force, so mv squared over r, is equal to mg cos theta. We can simplify this expression by cancelling out these m's, and what we can do is take this r up to this side to obtain an expression for v squared. So this gives us that v squared is equal to gr cos theta. So this is our first expression. The next thing we can say is that we know energy must always be conserved. Since the ball starts at rest on the large sphere, it has an initial kinetic energy equal to 0. However, it does have gravitational potential energy with respect to the second position, which we can take to have 0 gravitational potential energy. So we can say that the change in gravitational potential energy is equal to the change in kinetic energy. And as a result, we can create the expression that mgh, which is mass times the gravitational constant times the change in height between the first points, is equal to 1/2 mv squared. We can get an expression for this change in height by looking at this diagram. So we can say this is the initial position of the ball. This is the position of the small ball at the point we are trying to find out what the angle is. So we can resolve again and say that this whole angle here is equal to theta. We know that this length is r, so the change in height is this change here. And as a result, the change in height is equal to r cosine theta plus cosine 30. So what we can say is that it is equal to r cosine 30 minus cosine theta, because this is the initial height here and this is the final height, so we subtract the difference between them to obtain this change in height. So we can plug this in for h and say that mg r cosine 30 minus cosine theta is equal to 1/2 m. And what we can do now is plug this expression for v squared into here to eliminate this unknown. So it's equal to a half m gr cos theta. We can then simplify this further by cancelling out the m's and say that gr cos 30 minus cos theta is equal to 1/2 gr cos theta. Rearranging this expression in order to obtain theta, we get that cos theta is equal to 1/√3, and therefore theta is equal to arc cos 1/√3. However, we want to work out the change in angle between its initial position and final position, which means that we need to subtract 30 degrees from this angle here to get our final answer. So doing this in radians, we know that 30 degrees is pi/6 radians. So the change in the angle is equal to our final theta, so arc cos 1/√3 minus pi/6, which is equal to our final answer of 0.41 radians or 25 degrees.